Okay, thanks a lot for the kind introduction. Thanks a lot for having me here and hosting me so nicely. I'm very excited to be here and see so many faces interested in probabilistic logic programming and their applications. What I'm going to talk about is basically a combination of three different areas within AI. And on the one hand, you have like logic and relations, which are important to deal with a lot of applications. There is dealing with uncertainty, and then of course there is machine learning. And each of these has like particular traditions in AI and beyond. Like if you talk about relations, then you think of databases, of first of the logic of knowledge representation, also of programming. If you think about uncertainty, then you think about graphical models. And of course, if you look at learning, there's various ways that you can do that. You can learn parameters, you can learn structure. And this comes together in an area known as statistical relational AI, statistical relational learning. And today there's also like a related area, which is basically studying the same problem from a little bit of a different perspective, which is probabilistic programming. If you take the perspective of logic, then you fit both areas equally well. And that's the perspective that I will be taking. So let me start by arguing why relations are interesting. And I like to do that using a little example of games, where you basically have, in many of these massive multiplayer online games, you've got like states. And you can represent these states in a kind of graphical way as a network. There will be players in there will be cities, there will be alliances. And this will not just be something static, but it will basically evolve over time. And so what you have is like a dynamic graph that you need to represent and that you want to do something with. Possibly in a situation like that, you might want to learn models that will tell you how what's going to happen in the future, basically. That will allow you to predict what your opponents will do. And if you have these models, then maybe you can learn them you can use them to play better. You've got very similar situations. If you look at tracking people in a room like this, then basically what you'll see is that there are people that will form groups, and then they will also like maybe talk a little bit to one another. They will then also, and also that is something that will evolve. And again, you see that there is a little graph structure, like one group forms and people are close to one another, and then, okay, that evolves over time, basically. Again, you may want to predict that. You want to predict maybe the activities, how things will evolve. We're also looking a little bit into robotics, where we're looking at grasping objects that are on the table and maybe ordering things on the shelf. And what we're trying to do there is also like taking into account the relationships amongst the objects. Like, for instance, if you want to put something in here, it's quite easy. But if you want to move that same object in there, then you first have to make place. And so you have to reason about the objects, basically. If you look at systems that read the web, like the never-ending language learning system at CMU and many others by now, then basically what they do is they extract relationships between entities. And what they also do is like they assign a kind of certainty factor to these relationships. And basically what you get is a probabilistic database. You could look at networks that involve authors. And if you look at the way that people are cited, then they are cited in many different ways. My name you'll find in many different versions. And one of the problems is like to do entity resolution. That's like decide which of these different variations refer to the same author. There's social networks where you can do viral marketing. If you've got a situation like this where there's people that are friends to one another and these relationships are indicated by the edges in the network, then maybe you want to decide who you can best market in order that you will maximize the number of donuts that you will sell. If you look at networks, again, there's a lot of different entities and a lot of different relationships that play. Here you see the BioMine database, which was gathered in Helsinki by my colleague Hannu Toivonen, and he basically crawled the web and automatically constructed a pretty large biological network containing a couple of million of nodes and a couple of million of connections, links between them. And what he also did was like make that network probabilistic. Because he crawled it automatically, he put probabilities on the relationships because he was never sure whether they were genuine or just by accident. Now, in all of these situations, you see the need for objects, entities, and you also see the need for relationships. In many cases, it will also be useful to use background knowledge. And in many situations, it will also be very useful to cope with uncertainty in the data. I mean, in many of these situations we've seen, like the probabilistic database, the never-ending language learning example, if you look at the tracking of people, there's always uncertainty that matters and that you need to take into account. And then, of course, you want to learn, you want to process the data in order to do something useful. And that's basically the area that I was talking about earlier on, statistical relational learning, statistical relational AI, and it's also very relevant to probabilistic programming, although there are subtle differences between them. What this area has contributed over the past 15 years is like a number of different formalisms that allow you to do this kind of reasoning and this kind of learning and inference. Today there is many different formalisms that exist. Many more than would fit on the slide. I mean, the slide you saw was probably the situation till about 2005, 2007. Now there's many more. And what I will do today is I will focus on one particular formalism coming from the tradition of logic programming, and that's the formalism that we've developed over the past 10 years in my university in Leuven, basically. The choices that we make there is on the relational level. We use Prolog, a logic-based programming language, to represent theories. Right? And here you see a little theory. What we will do as well is we make a certain addition to this logical programming language, and it's a very simple addition that we do. We'll basically make that certain facts become probabilistic. Each ground fact will become a random variable, and you can put the probability of these random variables. And then we'll also develop techniques to do inference, learning, and so on. The Problog is just one representative of a pretty rich stream of research that has been in existence for about 25 years. The first probabilistic programming languages date from about 92, 91, when David Poole was actually proposing this kind of semantics. The first learning system was from 95 by a Japanese person, Taisuke Sato, and since then there's been many variations. So what I'll do today is I'll try to give you a flavor of this probabilistic programming language and what we can do with it. And I'll then also talk about inference, learning, and if I have time, about dynamics and decisions. So let me just introduce it by a little example. On top right, you see basically two urns. They're filled with balls and colored balls. And then there is also a coin that you can toss. And let's play a little game. There is a biased coin that we can toss. And we can draw a ball from each of the urns. You win the game if it comes up heads and there is a red ball, or there are two balls of the same color. Now, if you want to represent this little game in Prolog or Problog, you're gonna do it as follows. You're gonna have one random variable corresponding to the coin, and you say the probability of heads is 40%. That means the probability of not heads, tails, is 60%. Then if you draw a ball from the first urn, then there is 30% probability that it comes out red, 70% that it comes out blue, and that's what we call a choice or an annotated disjunction. You can do the same for the second urn, where there are 3 different colors. And then all that is left is basically define the rules of the game, and you'll do that in Prolog, or data log if you like. This basically says you win the game if it comes up heads and the color of one of the balls, I mean here you say I don't care which one, is going to be red. So that corresponds to the first rule. And this corresponds to the second rule. You win the game if the color of the two draws is basically the same. And so what you've got is probabilistic choices and then just plain logic programming to define the consequences. You can then ask a number of questions. You can ask what is the probability that I'll have a win. That's asking for a marginal probability. The more interesting question, the one that people typically are interested in, is like conditional probability. Given that I have some evidence, maybe I know that the ball I draw from the second urn is green. What's the probability that I'm going to have a win then? And people are also often interested in this MPE question, the most probable world where something is true. And I've talked about possible worlds. Let me show how you can generate them. And basically to generate them, what we will have to do is we'll go through all the possible choices that we can make and make a selection. So first, if I look at the first kind of fact, I can sample. And okay, in this sample, heads is true, and heads is true with probability 40%. Can take another sample, I mean from the second possible choice, where coming up red has probability of 30%. The third one has probability also 30% for the second ball. And then I've made all the possible choices, and all I have to do then is like do deduction with the logic, with data log, with Prolog, and I know that if these three things are true, well, I'm also going to have a win according to the rules of the game. And this is just one possible world. Of course, there is many other ones. I can basically select the tail. That's not head. Sorry. Slide shows. Right. I can take another one, and then I'll get up with this probability. And if I look at all the possible worlds, then they are sketched here. And this gives me my semantics of my program, because now I can basically answer all the possible questions. I can look at the most likely worlds in which win is true, and that's going to be this one. I can look at most likely world where blue, the second ball is not blue. That's this one. I can look at the marginal probability, the probability that you win the game. That's just looking at which worlds win occurs in and summing up their probability. And then of course I can do the conditional probability, which is going to be the most interesting one, where I basically look at the proportion. Well, I look at the probability of the evidence, that's the blue ones, and I look at the probability of the query, and I divide the two probabilities to get this one. Of course, this is not this is not the way that you should solve things. I mean, inference, it's clear that this is exponential and that this is not going to work. There's also an alternative view that's kind of instructive if you want to go to continuous distributions. Basically, it's illustrated in this little alternative notation, where you get a kind of tree structure, and here you see that you really have a generative model. Initially, nothing is in there, right? And then we know that John throws with probability 1. So here we've got just John throws being true. We can then look at if John throws, it's going to break with probability 60%. And so in this one, there is John throws and the windows break. Here is just John throws. And so we can actually iterate this procedure until we get this tree, and that the leaves will again end up with possible walls. We can then look at what's the probability of break, and again we have to look in which of these leaves, in which of these possible walls it occurs, and look at their probabilities essentially. The reason I'm showing this is that you're typically also interested in continuous distributions, and there is a variation of this formalism that we introduced in Leuven, and that's very much inspired on Stuart Russell's blog, another probabilistic programming language, where you can define things like this. If the type of an object is glass, then the length of the object is going to be Gaussian distributed with mean and standard deviation being specified. Once you've got that, you've defined this kind of random variable, you can then you can refer to that in your rules, where you can encode background knowledge, like two objects are stackable on top of one another if the length of the bottom object is larger than the length of the top object, and similarly for the width of that. What you get with these distributional clauses is basically also a generative process, like in this representation. The only difference is that whereas here you've got it all discrete, now you're going to get infinitely wide trees, and so you're going to have to do other things than just sum up probabilities. You have to do integration, and basically that's not going to work. You have to do sampling basically, and that is the predominant paradigm, I think, in probabilistic programming today. Okay, this is related to many different formalisms. There is an area called probabilistic databases, where people are basically extending traditional relational databases with probabilities, right? They just add a probability to tuples and then use SQL to query that. And so the semantics of that is very, very similar to what I've shown. It's just that if you use Prolog, you've got a programming language. If you use databases, well, you've got a database language. And that's what you've got in underlying NEL, in a sense, this never-ending language learner. If you want to try out Problog, I would like to refer you to our webpage. There's an interactive tutorial. You can type in little programs, and you can directly evaluate them, and you can directly see what is going on there. There's other programming languages that are probabilistic, and I guess Tom is the right person to talk about that, because he's been in this project, the DARPA project on this. There's many of these other languages. One of the famous one is Church. It's a functional programming language, and it also has added primitives to do probabilistic reasoning. And here you see a little example, whereas this would be like a normal scheme program. This would be like a probabilistic variation where there is like one primitive that flips a coin, and that flipping a coin is similar to like a random fact with a particular probability in a sense. And you can then also see that the outcome of such a program will be stochastic. You can also define a generative process, and you can do inference and learning for that. Here is like the Church equivalence of the gambling example that I was giving. But in the interest of time, I won't focus too much on that. Let me rather go to inference. In logic, there are actually two ways to do inference. One way is that you would take a proof theoretic perspective, so you would prove certain things. The other is that you generate models. I mean, like if you look at SAT, then you're interested in looking for models. And both ways you can actually apply on these Problog programs. It's clear, I think, that while generating all the possible walls is infeasible, And so what people typically do is they use this logical reasoning, either the proof theoretic or the model theoretic way, to come up with explanations as to when something will hold, then turn that into a data structure using knowledge compilation, and on that do then the probabilistic inference. So let's look at a little example. Here you see one of the traditional examples also from the field of statistical relational learning, where you basically say if you are stressed, then you smoke, and if you're influenced by somebody, then you smoke as well. And then there's some probabilistic facts, like Anne being stressed with a particular probability, one person, Anne, influencing Bob with another probability. And then you can actually ask, what is the probability that Carl smokes? And what you do then is you build up a proof tree. I mean, here you see, well, Carl smokes. Well, this proof basically fails, right? Because Carl is not stressed. It's not given that Carl is stressed, so this proof basically fails. There is other proofs, like this one, that succeed. It's basically backward chaining through the rules of the program. And what is then tempting to do is that you look at the probabilistic facts that are used in that proof, and the probability of that proof will basically be the product of the corresponding probabilities of these facts. That's all fine, because we only have one proof. In general, there might be multiple proofs, like if Bob is stressed, then you'll see that there's an alternative proof. And at this point, well, the probability of the other proof is listed here. It just depends on these two facts. And at that point, it's kind of tempting to say, well, let's simply add these probabilities. But if you do so, you will end up with probabilities that are higher than 1 in many cases. And so in order to avoid that, you basically have to solve what is called the disjoint sum problem. What is happening here is basically that there are certain situations which are true for both of the proofs, and so you have to be careful that you will basically exclude them. Here you see all the possible ones, and there you see the ones in which the first proof holds. Here you see the ones in which the second proof holds, and they clearly overlap. And so, well, you know, if you want to compute the probability of these two, you need, in a sense, what is called the disjoint sum. You need to subtract the intersection of the two proofs, because otherwise you've counted it twice. And the way that people are doing this is simply to use what is called knowledge compilation. There are two proofs, there are two conjunctions, so it's either this one or that one, and that's a logical formula. There is excellent techniques from the field of knowledge compilation that will basically produce good data structures, like binary decision diagrams, OBDDs. And on these OBDDs, you can then efficiently compute the probability, basically. BDDs are popular in many branches of computer science. I think the paper by Bryant was at one point the most cited one according to Cites here, so it's a pretty influential one. The cool thing is that it automatically disjoins the proof and solves this problem. I must stress that there is other representations that exist, and BDDs are not used anymore in the field. We use the more advanced things, like first we use BDDs, then we went to a more clever, more actual one, which is the DDNNFs, which is the one that was used for Bayesian networks, developed by the group of Anand Darwish at UCLA. And since the last 2 years, we are focusing on SDDs, and again, that gives us a speed-up factor of about 10 every time you change that process. Okay, the other approach, and I'm going to simplify that, is one where you basically ground out the program, like what you do here. I mean, you turn the program directly, you ground it out so that you fill out the necessary constants. You get a ground theory, and then the ground theory, on that one you will use weighted model counting solvers, as is also done in some other fields. And this again gives you speed ups if you do it this particular ways. This is a DDNNF. Should stress that exact inference is intractable. I mean, the problem is like hash p complete or sharp p complete. It's counting problems. They're hard to handle, and that's why there's also a lot of work on like doing approximate inference. And what people use a lot in the field is MCMC approaches. Especially this is popular, and sequential Monte Carlo is popular in the field of probabilistic programming. Okay, that's for what concerns inference. People are learning this. What does learning mean? There's two ways in which you can learn. First of all, you can imagine, well, in all cases you'll need data sets. And you can learn simply the parameters, in which case you start from a program like this one, and you then try to infer the parameters. And the way of doing that is very similar to what is happening in the graphical model community. You use like expectation maximization and related techniques to basically infer the probabilities. You can also do rule learning. I mean, suppose that you just have the data but you don't have the program. Then you can also learn the structure of these programs. And one way in which you can do that is by learning rules one after the other. We've developed like a kind of upgrade of the standard rule learning technology to learn problog programs. We've applied that to subsets of the NEL database, and we were able to come up with pretty reasonable rules. So in NEL they start with a database of facts, and they're interested in like learning rules that will allow to infer additional facts, basically like which athlete plays for which team and stuff like that. And again, I should stress, we're not the only ones doing this. Actually, the team at CMU is doing this in different ways than we do, for different types of representations, basically. Okay, let me come to the last part, which is about dynamics and decisions. Let me first start with the viral marketing, where we've developed a version of Problog that is making decisions. It's called Decision Theoretic Problog, DT Problog. What it does is it will basically allow you to maximize the expected utility by selecting certain facts to be true. So here you've got a network. If you sell a donut, you get +5. If you target somebody with an ad, you will pay $3. And you can represent this problem as follows. You've got your little network, which is just 4 persons. That's the entities, the friend relationship, that's the links. Then you're interested in deciding which persons to market. And so for every person, you need to decide, is it going to be true or false? That's a decision fact. That's the target that you want to optimize. Then you've got your Problog program, which basically says that if there are 2 friends, then the probability that they will buy from trust is like 30%. The probability that any person will buy after marketing is 20%. And then there is like the 2 rules that give background knowledge about this program. There is also the utility facts. What does it cost? I mean, if I buy, I get a utility of +5. if I market somebody, there is a cost of -3. And then what is happening is basically I can generate possible walls as usual, conceptually at least. I can generate that, and I can look at the utility which I get for this particular world. I see I've marketed 2 persons, so a cost of -6. 2 persons buy, so the utility is 40%. You can then also look at what's the probability of this world, and so the expected utility, well, the utility, well, if I sum over all possible worlds, I'll get the expected utility for these 2 facts. The question then is, can I find the optimum facts? And you can do that, which is of course also very expensive, but we use a kind of local search strategy to do that. We have applied that onto a number of problems in biology. People are at Leuven, our biologists are quite fond of this. They basically use that to analyze their data, and what they do is they will first look at a kind of interaction network that you can find in the literature, and then based on their data they will turn that network into a probabilistic one. And what is then happening is that you want certain interactions to be present, others you don't want to be present, and so what the deep problog then is doing is basically it selects the best subnetwork that maximizes the expected utility. And the biologists are pretty interested in that. We're also interested in using probabilistic programming to do problems with MDPs and relational MDPs, and I guess that's a known topic here, given a lot of work by Scott and also a lot of work by Prasad and by Tom, I think. First thing you can see is that it's very easy to represent an MDP in this distributional clauses. Basically, you can specify conditions, preconditions for actions. If conditions hold at time t, you can say what's going to happen at the next point. You can specify rewards, you can specify when to stop. So it's pretty straightforward to represent kind of dynamic problems within this distributional clauses. And let me illustrate it on a little example, which is about magnets that interact with one another. Well, objects interacting with one another. You can have objects that are magnetic, that are ferromagnetic or non-magnetic, and on the basis of their interactions they will have different behavior. And one of the games you can then do is you can look, if I have 3 objects that will interact with one another because I will push them closer, what is going to happen? Can I actually infer the nature of the object or the class of the object, magnetic, ferromagnetic or non-magnetic? And by writing a little program that looks as follows, you can actually do that. Initially, the type of the objects are assumed to be equally distributed. You can specify what it means to attract or to repulse, and the effect it will have on the positions of these objects. And what you can then do is basically simply do this kind of experiment. So this was with a little camera on top, where here you've got the initial situation. And then it should start interacting, right? And so you see they come close, but there's no interaction. Still you see that the probabilities are evolving. And what is nice at the next point is that now there's only 2 possibilities for each of the objects. and you'll see that the third interaction will basically make the conclusion, right? There's an interaction there now, and you'll see that for all three, you can be almost certain that the nature of the objects. There's other things you can do. We've played around with boxes, like tracking boxes, where you put a lot of boxes into one another and then you move them around. Because of the use of the relationships, you can cope with the occlusion and you still know where the objects are, basically. Things we've been doing in a robotics context is basically looking at probabilistic models of what is called affordances in robotics. What is an affordance? Well, an affordance tells me what I can do with certain objects, like this object affords being picked up, being opened, and being drunk, at least if there's water in there. And so before we started looking at this, people were using like Bayesian networks and single objects for this. And then the idea was that if you observe the effect and the object, maybe you can predict the action. If you observe the action and the effect, maybe you can predict or infer the object. And so there's like this three-way relationship between action, objects, and effects that you can use to do activity recognition, to do prediction, and so on, basically. And so we lifted that, in a sense, to multiple relations, and there's been a series of papers in the robotics literature where we've actually looked into that in various ways. And the idea was basically that you look at what happens first if you do actions on single objects, and then you gradually increase the difficulty of the situation, and you basically learn that. There's more videos. Affordances are also like having numbers. I mean, basically the goal is to look at displacements of objects and to learn about that, not just to do this in a discrete case, but to do it with the full complexity of the setting. And you can also learn models in that kind of situations. Then in the proper style of MDPs and relational MDPs, we've developed a planner to work with this kind of representations, and it's being used to do little grasping exercises with Kinova. If you're interested in that, you can talk to me later. But in the interest of time, I think I should probably conclude. So I hope I've given you a flavor of this area called statistical relational learning. I've also talked about probabilistic programs, about learning. There's many languages systems out there. There's still a lot to do. I think it's an excellent area for PhD students to work on. And there's cool applications coming up. I mean, I just gave a little flavor of some of the emerging applications. There's many, many more in the AI literature and in the natural language literature. If you're interested in finding out more, please check our website. You can really try Problog online without having to install anything. Thank you. Are there any questions?
So you mentioned that in the probability database you use SQL. Have you tried using NoSQL to try to construct a probabilistic database, or has there any work been doing it using NoSQL?
Well, people use any database language, but I think conceptually people have mostly used SQL or Datalog to do things, and they talk about, I mean, the typical theoretical database languages, like, I mean, I think Datalog is the most used there, and then not even the non-recursive one, because as soon as you go recursive, it becomes harder. And so there's complexity results and things like that.
I recently saw a video by Pedro Domingos who talks about 5 schools of cognitive machine learning, it seems like you've covered through the relational and the
Right.
Bayesian. And then he also talks about connections, which is deep learning, neural networks, and analogist, which is SVMs,
Right.
and genetics, or genetic programming, evolutionary learning. So, just curious if you
That's a
have any
fairly
thoughts.
general question. I mean, let me answer it from my perspective, which is, okay, as Prasad said, I've always been studying relational learning. There do exist like kernel extensions, so like the analyzers from that Pedro is talking about. There do exist combinations of that. There do exist also combinations with genetic algorithms, and there also exists neural network versions of that work with logic. So there's combinations of these.
I was just curious,
Yeah.
what, like if you were to extend this by with one of these paradigms, what difficulties would you see like extending your system to add one of these paradigms?
Yeah. Well, I think most of the combinations are basically combining two things, not three yet. I mean, I think also if you look at the graphical models, neural networks, there's connections, but still.
Can I say the programming, probabilistic programming language is still within the scope of Bayesian network, and the only thing is it has much more random variables, so the inference and the learning becomes difficult.
So inference is definitely the open question. I mean, so most of the people are really working on inference to speed it up. There's also something that I didn't talk about, which is lifted inference. Like, okay, in most of the approaches, one assumes like a fixed number of entities, and one grounds out. One needs to enumerate them all in the techniques I've shown here. But there do exist techniques that work like in a logical way. If you do a proof in logic, you don't need always to ground out. And so there's the open question of the domain is basically how you can do lifted inference that generalizes over the number of objects without enumerating them all in a sense. So that's like one of the focus of research, certainly in the statistical relational learning community. I think the probabilistic programming community is not really tackling that part.
I mean, can I still say it's a Bayesian network, right?
So you can represent Bayesian networks in this kind of representation. This is just much more expressive.
Okay.
I mean, it's way more expressive, basically, because you've got a programming language. I mean, a Bayesian network is basically a propositional representation. There's a fixed number of variables.
Okay.
Here you can represent, well, any program, so you can do more.
Okay.
And that's the power. But expressiveness always comes with the challenge of doing then efficient inference, right?
Thank you.
Prasad?
Yeah, I'm wondering how the Problog kind of family relates to the other family, which is golog and BT log and TT golog and variations of that.
That's a good question. I mean, I'm not an expert in golog and these. I mean, this is really like a very simple idea. I mean, just a logical variable is a random variable, and you attach probabilities to facts, and that's all you need, basically. So it's very, very simple. I think what they've done in golog and these things is a bit more complicated.
Well, a lot more limited. So, I mean, this Prolog is so much more expressive. Prolog is so much more expressive, right? There's no hybrid variables in golog, and
Yeah.
extremely limited. I mean, it's way more expressive.
Yeah.
Can I ask last
Yeah.
question? Or maybe
There's more time.
Lifted inference. I spent 10 years trying to do this, my thesis and beyond, and I really got discouraged, right? That you need to do it effectively, you need symmetries.
Yeah.
And when you have a lot of evidence that you do in practice, you break all your symmetries.
Right.
And despite Peter Dominguez saying, no, you can do it, I don't believe him.
Yes.
Can you convince me that it's not a dream?
So what? Okay, I mean you're right. As long as you stick to exact inference, you're gonna hit limitations. And I mean, like my former student Guy van den Broek, he's shown some negative results which you get quite easily. Well, I mean, which are very simple cases where these occur. You don't get these results easily, but I mean, but what these people that really study it claim that you need to do is to combine it with approximates. And like if you do probabilistic reasoning, and you can make, I mean, you do need approximate reasoning, and not just approximate but lifted. I mean, that's the future, in a sense. And what they then do is like instead of looking for perfect symmetries, they will look for approximate symmetries. If a symmetry holds in 1 million of the cases, but not in the next one case, it's probably okay to assume it's symmetric and do things like that. And so that's what everybody says is the future. We'll have to see in 10 years or in 5 years, but people are making progress. So people are making progress.
So probabilistic programming sounds that the user has to write the program. Is rule learning not as important in this case?
Yes. So I didn't do justice to all of the probabilistic programming people, because what they do, like the people doing church and like a lot of the Americans in the DARPA project, what they do is they would write like indeed models as programs, and would then use a Bayesian learning approach. Right? They would put the prior like on the parameters, and then with the data they would actually tune the parameters automatically as well. And so that's the paradigm, that you write down models. They're more complex than the traditional models you've got in the machine learning literature, because you've got this expressive power that is increased, and then you try to do Bayesian learning or other learning techniques. I think that's what a lot of people believe in today.
So it's more that the user provides the models and then whatever.
Yeah. Structural learning has not been tried so much in probabilistic programming. That's more something again that people do in the SRL community. But yeah, differences are subtle, I think.